Till now in quantum mechanics classes we have considered the relativistic theory due to Schrödinger, and we have also solved few examples as for example harmonic oscillator problem and orbital angular momentum problem using matrix mechanics techniques, that is by introducing raising and lowering operators. Now, our curriculum demands the discussion on spectroscopy. The entire spectroscopy depends on the concept of spin, and in classical mechanics, in classical quantum theory, there is no concept of spin. The concept of spin comes from relativistic quantum mechanics. Furthermore, the discussion of fine structure of hydrogen atom. This fine structure spreading of energy levels arises due to relativistic effects. So, to give a brief idea of the relativistic quantum mechanics, we shall discuss few topics under the heading Advanced Quantum Mechanics. Firstly, we shall discuss relativistic quantum mechanics. We shall not go into the details of the mathematics involved. We just briefly describe what happens, and in most of the cases we shall write the final result. And secondly, we shall introduce spin, how to define spin operator in quantum mechanics. In the third class, we shall discuss how to add two angular momenta vectors, and finally we give you a brief flavor of perturbation theory. So, this is the plan, and then with this introduction we shall come back to spectroscopy part. Now, time independent Schrödinger equation, as we know, that this is minus h line square by twice m h cross del psi del t of RT. This is the time dependent Schrödinger equation. This is not relativistically correct. This is not a relativistically correct equation, as it involves first order derivative, partial derivative with respect to time, while second order spatial derivative, as it involves del t and del 2, del x2, etc. So, this is a serious objection, and we found that the theory could not be applied to particles, to microscopic particles moving at very high speed. So, we are to take into account the effect of high speed also in microdomain. So, this is the topic known as relativistic quantum mechanics. The easiest way to include relativistic effect is to replace this classical expression of energy for a free particle. In classical mechanics, the energy expression for a free particle is this, and this is replaced in quantum mechanics in relativity is m squared c to the power 4 plus c square p square, where m is the rest mass energy. Rest mass. I am just not writing m0 because in our discussion m will not appear, so m stands for the rest mass. Now, what we did in Schrodinger picture, we used a correspondence principle due to both to replace the dynamical variables by their corresponding Hermitian operators. So we did it I h cross del t operating on psi is equal to minus h line square by twice m nabla square operating on psi. This is the Schrodinger equation for a free particle. Here we also do the same thing. We write I h cross del t for E operator. First we use Bose correspondence principle to replace the dynamical variable by their corresponding operators, and we define an operand. You see that there is no dynamical variable, so it is an identity operator minus IH cross nabla psi, or minus h line square del 2 psi del t2 m square c to the power 4 psi minus c square h line square is the new relativistic equation for microparticles. This is a relativistically correct equation because it involves second order derivative with respect to time as well as in space. This is a relativistically correct equation. Correct equation as it involves del 2 del t2 and del 2 del x2 etc. This equation is known as klein-Gordon equation. Klein-Gordon or Schrodinger's relativistic equation. Once we get this equation, our temptation will be to see how the probability current density, which is the which signifies the conservation of probability, looks like in this Klein-Gordon equation. So we start with Klein-Gordon equation and try to arrive at the equation of continuity. We start with this equation. So this is m square c to the power 4 psi. I am not writing the argument of psi, c square h line square the Hermitian conjugate equation is this is the Hermitian conjugate of this. Hermitian, the Hermitian conjugate of first equation is this. We multiply this from the left by psi star and the second equation from right by psi and subtract the second from the first. These two terms cancels out because it becomes psi star m square c to the power 4 psi for each of this. Coming to this term, this is minus c square h line square. From the first term it is psi star nabla psi. From this term it is And from the second equation it is h line square minus h line square is we can get rid of, or we write it as divergence of psi star grad psi minus. In doing this, we have first term is psi star nabla square psi, which is this. The second term is, it has a term like this, and here we shall get a similar term with negative sign which cancels out, so that the result is this. And c square has to be adjusted 1 upon c square. Similarly, this side can be written as psi star del t recall the probability current density that we introduced in our class non-relativistic theory. It is the divergence of J, that is, we write H cross by twice Mi this quantity is J, and we are to adjust the same thing. So H line 2 Mi by C del T of psi star or we write it as divergence of J plus del rho del T is equal to 0, where the probability current density is same as we have used it in twice Mi. This is same as we used in non-relativistic theory, and this. And the probability density is different, where rho is, you see that if we take I on the numerator, it will be minus, which adjusts to IH cross 2mc square, sorry, this should be c square, c square times psi star del psi del T minus del psi star del T psi. This is probability current density, and this is the probability density. You recall that in the case of non-relativistic theory, we argued as per Born interpretation that rho is equal to psi star psi is essentially non-negative quantity. In Schrödinger equation, Schrödinger's theory, rho is equal to psi star psi is greater than equal to 0, and we interpret it as the probability density. Here, rho could be positive, 0, as well as negative. So, rho cannot be interpreted as the probability density, although the probability current density is same as in the case of non-relativistic theory. But in that case, the interpretation of the wave function will be a problem. This is one of the serious drawbacks of this theory, of the klein-Gordon theory. However, If we try to get the energy eigenvalues, we can get the energy eigenvalues from klein-Gordon equation. Free particle energy, or rather we shall call free particle energy as per klein-Gordon equation. We recall that in klein-Gordon equation the Hamiltonian is written by E square. We have E square is equal to m square c to the power 4 c square p square. If we replace E by h cross omega and p by h cross k, we get h cross omega is equal to plus minus m square c to the power 4 plus c square h line square k square under root. So the energy is either greater, so free particle energy, if E is the free particle energy, then it is either greater than plus mc square or it is less than minus mc square. And this negative energy increases with increasing k. So to say, the energy spectrum would be like this. This is zero value of k, so it is plus mc square and then it increases like this, and this is minus mc square and then it increases like this. This is the energy, free particle energy. This much of energy is not available. This energy gap is twice mc square. A free particle cannot have energy in this band, so it is called a forbidden band. And this was found to be astonishing or something surprising, that the energy, the negative value of energy increases with increasing k. Later, and if we could take a particle from a positive energy state to a negative energy state, then we could get a huge amount of energy, which seems to be unphysical at the time of Klein-Gordon, at the time when this theory was proposed. Rather later on, it is found that these are the energies of particles, that is for electrons, say for electron, and these are the energy for antiparticles, say for positron. This is one part of the Klein-Gordon theory. That another thing is that if we could apply the Klein-Gordon theory to the hydrogenic atom problem, then after a detailed manipulation we could get an expression for energy. For hydrogenic electron, it is found that Klein-Gordon theory gives energy. Klein-Gordon theory gives an energy where E depends on NL, which is equal to E Bohr's theory, energy as per Bohr's theory, plus delta E K. We write it as this. This is the energy as per Klein-Gordon theory. This is the energy as per Bohr's theory, and this is the correction term. This delta E kg of NL is found to be one plus Z square alpha square n square times n by L plus half minus 3 by 4, where alpha is equal to 1 by 1 upon 137 is the velocity of electron in first Bohr radius Bohr orbit by velocity of light c. It is called fine structure constant. For a given value, so here we see that the energy level depends on N as well as on L. As per Bohr's theory, the energy level depends only on principal quantum number. You recall that E Bohr N was minus RCH upon N square, where R is the Rydberg constant. Here in klein-Gordon theory, we see that the energy level do depend on N up together with it has L dependence. For a given value of N, there are N values of L. For a given value of N, L ranges from 0 right up to N minus 1. So a particular energy level, Bohr energy level, is split into N levels as per klein-Gordon theory. This is the fine structure splitting of energy levels as per this theory, klein-Gordon theory. As for example, if we have a S level, this is the Bohr's theory, and as per klein-Gordon theory, there is only one value of L, so there is no, the energy level, we will get only one energy level, although that energy level will have a shift, because if we put L is equal to 0, there will be an N dependent shift, so we will have a one line. It will be just shifted below. If we have P levels, say this is the Bohr's level, then P level, once we have L is equal to 0 and once we have L is equal to 1. Sorry, if we have N is equal to 2, then we have two values of L. For N is equal to 2, we have two values of L. One is L is equal to 0, another one is L is equal to 1. So this energy level will be split into two energy levels. Similarly, D levels will be split into three sub-levels. These levels, or this energy splitting of energy levels, is due to the relativistic effect. As we shall see in our next lecture afterwards, that when we include relativity, then there are certain effects are included in the theory. One important thing is the spin, and the splitting of energy levels due to the relativistic effect is called the fine structure splitting. So this is the fine structure splitting of the energy levels as per klein-Gordon theory.